Hi students, in today's session I am going to discuss the assertion and reasoning type of questions from the chapter alcohols, phenols and ethers, and please watch the video without skipping because I have selected 17 unique questions. Okay, so you know, 4 options will be given if assertion and reasoning both are true and they explain. If there is a proper explanation, then it is option A. If assertion and reasoning both are true but reason is not a proper explanation of the assertion, then you have to choose option B. If assertion is true but reasoning is false, then option D. When assertion itself is false and the reasoning is true, then you have to choose option D. Okay, so first begin the question. Question number 1. Ortho and para-nitrophenol can be separated by steam distillation. This is your assertion. Okay, so let's discuss this first. See, this is your ortho-nitrophenol. Okay, and this, what is this? And this is your para-nitrophenol. And this is your para-nitrophenol. And as you see, this molecule is capable of undergoing hydrogen bonding. See, this hydrogen is attached to an electronegative group, and nearby itself we have an electronegative group with lone pairs. Okay, so hydrogen bonding takes place. Okay, here what happens, this hydrogen is capable of undergoing hydrogen bonding, but what will happen, since this group is not near, it will form the hydrogen bond with the adjacent molecule. Okay, like this there will be a network. In para-nitrophenol there will be a network among the molecules. Okay, there will be a network. This is one molecule. Okay, but here the molecules will not associate because see, this is intramolecular. Okay, see, there is an association between a molecule and another molecule. This goes like a chain, so there will be a network. Okay, more the network is, more will be the melting point. So because you have to supply more energy to overcome all the interaction forces. But here in intramolecular hydrogen bonding, intra means within the molecule, so it will not associate with other molecules. So these molecules remain separated, so easily it will melt. See, its melting point will be around 45 degrees Celsius. So what will happen during the steam distillation? In steam distillation, this mixture will be taken along with water. You know, the boiling point of water is 100 degrees Celsius. Since the melting point of this isomer, the ortho isomer, is 45 degrees Celsius, it easily mix with the steam. Then when you cool it with a condenser, you will get water and the ortho isomer. Okay, and your ortho isomer is immiscible with water, so easily you can separate from water. Okay, so the main point is what? It is intramolecular hydrogen bonding, so its melting point is 45 degrees Celsius, which is very much lesser than the boiling point of water, so easily it will come with steam distillation, whereas its melting point is 119 degrees Celsius because it forms a network with other molecules. Okay, so assertion is correct. Reasoning: ortho isomer associates through intramolecular hydrogen bonding, while para-isomer associates through intermolecular hydrogen bonding. Yes, reasoning is also true. So, and it is a proper explanation. So, I am choosing the option A here. Okay, so here, assertion, this is a tertiary butyl methyl ether, gives tertiary butyl iodide and methanol on treatment with HI. Okay, see here, this is a kind of ether. And this is HI, it is an acid. See, any ether, if you treat with HI is an acid, isn't it? So what happens here? Your ether, the oxygen present in the ether has lone pair here, and immediately what is the first step? Protonation takes place, isn't it? Okay, in case if this R and R dash both are either primary or secondary, what happens in the next step? Your bulky iodine group, okay, approaches the least substituted carbon. Okay, the least substituted carbon, and it will break. So soon after this protonation, the oxygen bond becomes very weak because here the valency is 3, so it has to break a bond, and by this time your iodine approaches any one of this. Okay, depends on which is least substituted. So your Ri plus R dash OH will be formed. So this follows SN2 mechanism. Okay, provided your alkyl, both the alkyl groups either primary or secondary. But here, what is the ether here? The ether present here, it is one of the alkyl group is tertiary in nature, isn't it? So the first step takes place as usually, okay, protonation. So when you add acid, it is the electrophile and the nucleophile which reacts. Your proton will search for any nucleophilic site and your oxygen has the lone pair. Okay, immediately protonation takes place. But here what happens, due to the tertiary nature of this alkyl, you know, the tertiary carbocations are very stable. Immediately before the approach of iodine itself, this bond breaks. In what fashion? Your carbon gives the electrons belonging to this bond to the oxygen, and it goes as tertiary carbocation. Okay, CH3OH. Okay, CH3OH. So then after this step, your iodine comes and attaches to this electrophile. Okay, so here it takes place in two steps, so it follows SN1 mechanism. Okay, so the reaction occurs by SN1 mechanism. Both assertion and reasoning are correct, and it is a proper explanation. So this also option A. Okay, so here in assertion, the carboxylic acids are more acidic than phenols. Okay, so let's discuss this. See, this is your carboxylic acid. This is your carboxylic acid, and this is your phenol. Okay, we know that. Okay, phenol has an acidic proton. Your hydrogen is attached to a more electronegative group. Okay, so easily it will donate proton. But what is the assertion here? The carboxylic acids are more acidic than phenol. Let's analyze this. Yes, see, I told you always the acidity of phenol or any carboxylic acid. Okay, I told you that it is inversely proportional to the electron density of the oxygen, the load. Okay, so what happens here? Here, what is the difference? The presence of the carbonyl group. We know that the carbonyl groups are powerful electron withdrawing group. So what it will do? It will pull all the electrons from the oxygen here. So thereby what happens? The electronegativity increases, and what happens? It will pull all the lone pairs here. So electron density decreases. So it will increase the acidity. Okay, so the assertion is correct. Carboxylic acids are more acidic than phenols due to the presence of this adjacent carbonyl. The phenols are ortho and paradiene. This is also correct statement, but is that a proper explanation of this one? No. So it is option B. Okay, so ethers behaves as bases in the presence of mineral acids. See, what is a base, students? See, any base must abstract a proton. Okay, arrow in this, it must abstract a proton. For that, what is needed? We need electron density. Electron density can be lone pairs. It can be lone pairs or lone pairs or free electrons. Okay, and unpaired electrons, and it can be a nucleophile also. Okay, so here what happens in ether? The general formula for ether is this one. Okay, your oxygen has lone pair, 2 lone pairs. So immediately when you put any mineral acids, for example HX, so what happens? It is a source of proton here. So this lone pair will abstract this proton, isn't it? We saw in the cleavage of ether, isn't it? The first step is the protonation. So yes, ethers behave as bases in presence of mineral acids. Very true. In ethers, oxygen consists of lone pair of electrons. Yes, only due to this lone pair it acts as base. So I am choosing option A. Okay, so here methoxyethane reacts with HI to give ethanol and iodomethane. Okay, so what is methoxyethane? So CH3, CH2O, CH3. Okay, so here what happens here? See, both the alkyl groups are primary and this is a methyl group. Okay, so protonation takes place. First step is the protonation, and it has, your oxygen has 2 lone pairs of electrons. Okay, so now this oxygen has 3 valency, so one of the bond it has to break. Okay, now your iodine comes to play. This hydrogen came from this H. Okay, now the remaining part is iodine minus I minus. So what it will do, either it has to approach this carbon or this carbon, but you know iodine is a very fat guy. Okay, so he cannot approach here because it is attached to this carbon. So for this iodine it is little bit comfortable to approach this carbon because it is all the valencies are hydrogen, so it will go here. Okay, learn this, students. See, it is going to form a bond with this carbon. For that it is donating electrons. Okay, so the electrons belonging to this bond, okay, both electrons will go to the oxygen. Okay, so what happens? So this bond will be broken. OH plus methyl iodide. Yes, correct what they said. We got ethanol and methyl iodide. This is correct. Reaction of ether with HI follows SN2 mechanism. This is also correct, but is that a proper explanation why it happened? No. This is also true, so but the option B, it is not the proper explanation why particularly this product came. Okay, so next. Your sixth question, dehydrogenation reaction of alcohols is an oxidizing reaction. Okay, so let's see what happens here. Any alcohol, so I'm going to take this alcohol, so dehydrogenation of alcohol. So I'm going to write one of the hydrogen as this one. Okay, CH2. Okay, one hydrogen I'm writing it down, and this hydrogen also I am writing it down. Okay, so this is removal of hydrogen. Okay, dehydrogenation minus H2. So what happens here? I am going to get CH double bond. Oh, what is this? Actually this is this hydrogen is here. Okay, so this is your aldehyde. So this is your primary alcohol to aldehyde. This is an oxidation reaction. Removal of hydrogen is an oxidation reaction. Yes, correct. It involves loss of dihydrogen from alcohol. Yes, this is also true. It is the correct explanation of this one. So I am choosing option A. Okay, so the ethanol can be converted to acetaldehyde by treatment with pyridinium chlorochromate. So yes, see students, any alcohol, see this is your alcohol. If I oxidize this in the first step, as I told you, one hydrogen from here and one hydrogen from here, so CH3. Okay, so I'll write here like this. Okay, and one hydrogen here. Okay, so I'm going to remove this oxidation. So the CH double bond O, first step is aldehyde. If I over oxidize this, I am going to get carboxylic acid. Okay, so but I have to choose a proper oxidizing agent. Okay, this is like a express train and a local train, like that. If I use a strong oxidizing agent like KMNO4 or K2Cr2O1 potassium dichromate, it will not stop here. It will end up in carboxylic acid. But if I use a mild oxidizing agent like pyridinium chlorochromate, PCC, or MnO2 or CrO3, okay, I will get, okay, this is like a local train and this is like a express train. This is what strong oxidizing agent, and these are mild oxidizing agents. Okay, you can stop at each and every junction like that. Okay, please remember this: PCC, MnO2 and CrO3. Yes, PCC is a better reagent for oxidation of primary alcohols to aldehydes. Yes, very true. If you use very strong oxidizing agents like this one, you will not end up with aldehydes straight away. You will end up only in carboxylic acid. Okay, so this is option A. Tertiary alcohols do not undergo oxidation reactions. Yes, why? See, take a tertiary alcohol. See, in previous example what I said, I have to, here also I have to remove dihydrogen for oxidation. One hydrogen from here, and where I will get one hydrogen. See here, I took one hydrogen from this oxygen and one hydrogen from the alpha carbon. Okay, here the alpha carbon has no hydrogen, so no alpha hydrogen, so no oxidation. So you cannot oxidize tertiary alcohols. Correct. They do not have the required CH bond. Yes, what is the required CH bond? This alpha. hydrogen. Okay, I don't have. Okay, so this is option A. Okay, so next question. Vapors of primary and secondary alcohols are passed through heated copper on primary alcohol to aldehydes. Yes, so this is also a kind of oxidation reaction. Okay, so kindly recall. So I will end up with aldehyde here if I take a secondary alcohol. If I take a secondary alcohol, I will get a ketone here, right? Okay, so it is a dehydration reaction. No, it is not dehydration. Learn students, dehydration means minus H2O. Minus H2 means the term should be dehydrogenation. Okay, so it is not dehydration. Okay, so this is wrong. So option C. Then addition reaction of water to but-1-ene in acid medium. Acidic medium yields butane 2-ol. You see, what is but-1-ene? So but means there must be 4 carbons. In one position there is a double bond. Okay, so here also 2 hydrogen and 1, 2, 3, 4 hydrogen. Okay, so what happens here? I am going to add water in presence of acid. See, addition of water in presence of acidic medium has to follow Markovnikov's rule. So according to Markovnikov's rule, the nucleophilic part of water, what is the nucleophilic part of water? This is the nucleophilic part of water, has to go to the carbon which has least number of carbon atoms, isn't it? Isn't it? So this carbon atom. So how this bond will polarize? How this bond will polarize? So this is negative, so this carbon must be positive, right? So it will polarize in this direction. So the bond will polarize in this direction. So I will get CH plus, okay, then the hydrogen will take this position. Okay, so what carbocation it is? It is a secondary carbocation, and to this your nucleophile will come and attack. Okay, so what is the product you are getting according to Markovnikov's rule? You will get butane 2-ol. Okay, so this is the correct answer. The addition of water in acidic medium proceeds to the formation of primary carbocation. Is this a primary carbocation? No, it is a secondary carbocation. So this is false. So option C. Okay, so the paranitrophenol is more acidic than phenol. So let's analyze this. See, as I told you, your phenol, always remember the acidity is inversely proportional to the electron density. So in paranitrophenol, due to the presence of this electron withdrawing group, the electron density even decreases. So when the electron density decreases, the acidity increases. Okay, so this is correct statement. Nitro group helps in the stabilization of the phenoxide ion by dispersal of negative charge due to resonance. See, this is also correct statement. See, once the acidity, to calculate acidity straight away from the molecule, this is one method. The another method, you have to write the conjugate base. If this is an acid, this is the corresponding conjugate base after removal. Okay, so the more the stability of the conjugate base, if the stability is more, so this will be weak, in the sense it will not react at all. So the more weak it is, more weaker the conjugate base, more acidic, the more strong the acid will be. Okay, so this is your acid with proton. Without proton, it is a conjugate base. Okay, so how to calculate the stability? The O minus, okay, if it sits more on only one atom, the stability increases. But what happens here? Resonance increases. It will involve in resonance, and also due to the presence of nitro group, it will pull the electron density towards itself. So what happens here? It increases the stability. Okay, it increases the stability of the conjugate base. So what happens? So it will not react at all. If you are very stable, will you improve in your life? No. If you are not stable only, you will work for your life, isn't it? So the weaker the conjugate base, the corresponding acid will be more strong. Okay, so this is also correct. Okay, so this is option A. Isn't it, student? In our life also, if you are very comfortable in our life, if you are will we grow? So Same thing. Boiling points of alcohols are greater than ethers of same molar mass. So this is very interesting, students. See, I am going to take as this an example, ethanol and this ether. See, if you see the molecular formula is same, of the same molar mass. If you see this is an alcohol, this is an ether, the boiling point will be greater for this. Why? Because alcohols will engage in strong hydrogen bonding. For boiling point, students, first what you have to see, hydrogen bonding, then van der Waals force. Okay, strong hydrogen bonding. How many hydrogen bond it can form? See, the lone pair will be involved in hydrogen bonding, and this hydrogen will also involve in hydrogen bonding. Okay, so per molecule 2 hydrogen bonding, sorry. But in ether, if you see, it doesn't have any hydrogen, so no hydrogen bonding. Okay, so more number of hydrogen bonding, more will be the interactions, more the energy you have to supply, so the boiling point increases. So here no hydrogen bonding, so its boiling point will be very low. It will be very low. Okay, vapor pressure will be very high. So this is correct statement. Ethers can form intermolecular hydrogen bonding with each other. This is a wrong statement. So option C, ether can form hydrogen bonding with water. It cannot form hydrogen bonding with another ether. Okay, because there is no hydrogen here, but it can form with water. It needs proton to form hydrogen bonding. Okay, so like bromination of benzene, bromination of phenol is also carried out in the presence of Lewis acid. So this is a wrong statement. I will tell you why. See, here the Lewis acid, any Lewis acid, for what it is used to polarize or break any bond. Okay, so but in case of benzene, we don't have any functional groups to polarize this bond. Okay, so we have to polarize this bond, so because of that, so we have to get Br plus and Br minus, so the electrophile will come and attack here. But in case of a phenol, it has a functional group with a lone pair. This itself, it's sufficient to polarize this one. It doesn't need any additional Lewis acid. Okay, so this is wrong. Lewis acid polarizes the bromine molecule. This is the correct statement. Okay, so option D. Then orthonitrophenol is less soluble in water than the meta and the para isomer. We know the reason, obviously. See here, in ortho nitrophenol, it has intramolecular hydrogen bonding. Okay, so this hydrogen is involved with this nitro group, nearest nitro group. So when you put in water also, this hydrogen is not available to form hydrogen bonding with water. Only if it forms hydrogen bonding with water, it will be soluble, because organic molecules are not that much polar. Only due to, if it is capable of forming hydrogen bonding, then only it will be soluble in water. Okay, because they are very polar in or in non-polar in nature. Water is a polar molecule, but if it forms hydrogen bonding, it will be soluble. So since the hydrogen is already involved in intramolecule, it is not free to form additional hydrogen bonding with water. But in case of meta and the para isomer, what happens? Soon after you put in water, the water comes between each and every molecule. You may ask, ma'am, here also intermolecular hydrogen bonding takes place, but here also hydrogen may not be available. But what happens when you put in water? When the molecules interaction takes place, no, the molecule will come in between each molecule, so it breaks. So immediately what happens? Those intramolecular hydrogen bonding will break, and it forms new hydrogen bonding with this water, like this. Okay, with water molecules. So they have better solubility. Okay, they are increasing solubility in water due to this reason. Okay, due to this reason. So meta and para isomers exist as associated molecules. Yes, they exist as associated molecules. This is right. Is less soluble. This is right. But is that a proper explanation of this one? No. So this is option B. Okay, students, this is intramolecular. Intramolecular means you cannot break the bond, because within the molecule. Okay, here the water molecules comes in between. Okay, one phenol and one water, like that. Okay, but here the molecule itself, no, it is complete in itself, so it cannot interfere. Water cannot come in between the molecule. Okay, So ethanol is a weaker acid than phenol. So yes, see, this is your phenol. Any alcohol, I told you, the acidity is inversely proportional to your electron density. I told you here the electron density increases due to the plus R effect of the ethyl group. Due to this electron density increases, the acidity decreases. Okay, so this is correct statement. Sodium ethoxide may be prepared by the reaction of ethanol with aqueous sodium hydroxide. This is a wrong statement. I'll tell you why. See, what is sodium ethoxide? Sodium ethoxide is this one. Okay, so what happens, they are telling, see, just now we saw this is a weaker acid. Weaker acid means it must be stronger base, isn't it? Isn't it? So what happens when you treat ethanol with aqueous NaOH? In aqueous condition, in aqueous means water. In water, your sodium hydroxide will dissociate like this, isn't it? Will dissociate like this. So what happens here? What happens here? Even when you take this proton outside, when you take the proton out to form sodium ethoxide plus water, what happens? Here, this is a very strong base. Weak acid and a strong base. Then what happens? What is the duty of a base? It has to abstract a proton. It will react back with water and it will turn to this situation. Reverse reaction takes place. So you cannot prepare using aqueous sodium hydroxide. But then how to prepare this one? Treat this ethanol with metallic sodium without water. So in this way only you can prepare sodium ethoxide with the evolution of hydrogen. Okay students, this is very important, please remember. Not in aqueous solution, only the reverse reaction will take place. Then so what is this students? This is option C. A phenol forms 2,4,6 tribromophenol on treatment with bromine in carbon disulfide. So remember students, in presence of carbon disulfide, no 2,4,6 tribromophenol, only in presence of bromine water. Okay, bromine water only 2,4,6 tribromophenol takes place. In presence of, this is very important. Okay, so then and there you have to recollect, that's all. Okay, organic chemistry is all about remembering, recollection. Okay, then you have to practice. It is more like mathematics only. Okay, so you will get either, this is ortho and para. Okay, your para will be of major amount. Remember this. Okay, this is a non-polar solvent. Okay, water is a polar solvent. In the presence of non-polar solvent, you will get only monobrominated product. Bromine and carbon disulfide both are non-polar. So this is wrong, this is right. So option D. So phenols gives ortho and paraphenol on nitration with concentrated HNO3 and H2SO4 mixture. See, phenol when treated with these mixtures, it is a strong nitration reagent for doing nitration, and phenol is an excellent rich molecule. So you will get only trinitrophenol and not either ortho or paranitrophenol. Phenol group is in phenol, hydroxy group in phenol is ortho para directing group. This is correct, but this is wrong. So option D. Oh, thanks for watching students. If you like this video, please share along with your friends. I'll meet you soon with my next chapter. Thank you.